In the second part to topic 4, part 1, we're looking at phase differences. And for these phase differences, we'll be more specific about them when we get further into talking about phases. But I would like you to look at this link here. If you would go here and just read through this, I think it does a really good job of summing it up, and it follows stuff. Like you just talked about oscillations in the previous one, the description of them, and then it goes into some of the different terms and equations that you will be using throughout this topic. So I do suggest that you take a minute here and you read through the different types of terms that they have to discuss throughout these slides. Furthermore, I'd like you to look at the diagrams that they assess to these as well. These are really good. I actually pulled them out myself, so please make sure that you read this blurb, okay? Make sure that you're reading this blurb here so that you understand what is going on throughout this system. Okay, so jumping out of there, the key things that you're going to be looking at is in phase, out of phase, and interference. Those of you that have had physics before are aware of interference as being constructive, destructive, and complete destructive interference. So in that manner, we'll assess them a little bit further in more detail. So once again, here are the three that I really like to pull out of there. Please make sure that you do read those slides again. It'll definitely give you a good heads up, and as well as being able to answer some questions that you may have so far on this. But I like this because it's showing you very straightforward, like for instance your mass spring system, and then it shows you the oscillation of this with the sinusoidal graph, and then it actually shows you in circular motion what would this look like, the direction that the velocity would be heading, etc., etc. As you know, acceleration, centripetal acceleration is heading towards the center of the circle. They didn't draw them in there, but I'm sure you guys would be aware of that. Okay, so looking at these then, and we'll actually have the, I will have a setup of a simple pendulum and a simple mass spring system so you can look at the oscillations of them, and you'll also be working with them back in the lab. So with that in mind, on the left-hand side, you can see of a mass spring system, and they purposely put it on its side like this because then it's denoting frictionless, right? You don't have like that air friction or like air resistance, friction of air, that is working against this system if we were to take this guy and rotate him onto the side. And this way that if they were rotating up and down like this, there would be force of gravity and force of air resistance that would be working against the system. So we're going to keep it this way, stating that that is correct, i.e. frictionless plane. Therefore, technically, it should oscillate forever and ever and ever because there's nothing working against it, non-mechanical energy, to try to get it to slow it down. Okay, so with that in mind, let's read through this. Position where equilibrium position. It's the position where the pendulum bob or the mass on a string or spring would rest if not disturbed. So you would have your rest position. For instance, right here, we're looking at rest position because you're not trying to pull it, nor are you trying to compress it. Right here, you would have your rest position. You're not trying to pull it back so far and leave go, right? The natural length, another way of looking at equilibrium position, would be the natural length of any string or spring at which it exerts no force on the mass. No force is being exerted on the mass. It's kind of getting you to think about F equals ma, correct? Okay, so displacement at equilibrium position should equal 0 meters, right? Because you're not going anywhere. It's your relaxed length. I'm at rest. This is exactly where I want to be. So you shouldn't see a value written there besides 0. Okay, so let's analyzing, and you know the IV system, they use the S in that scenario instead of Z, so I'm trying to hold true with that. Oscillations on a pendulum. So the pendulum bob is pulled back to some distance here. Okay, it's pulled back to some distance, and it's released. It'll swing away from its starting position, past the equilibrium position, change directions, and then swing back past the equilibrium position, back to the starting position. So that would be one complete cycle. It'll repeat and repeat and repeat and repeat unless friction is present in the system. If friction is present in the system, then it will eventually come to rest at its equilibrium position. So you're going to look at different forces that are acting on the bob. The bob accelerates back towards equilibrium, which should make sense, right? Stop and think about this, guys. When you're holding that bob back at so many meters, centimeters, whatever, from the equilibrium position, you have all that stored energy. It's all potential energy. And then you leave go, the velocity is going to increase because the kinetic energy increases. Therefore, you'll have an acceleration. So it's going to be moving the fastest when it's at that equilibrium position and it swings back past, and then, oh, I'm going opposite direction of motion. So you have this force that's working opposite the direction of motion, which is in essence going to make the pendulum bob slow down, i.e. come to rest at the complete opposite side of where you released it from. Then it's going to swing back past equilibrium back to its starting position. One complete cycle has occurred here. Process continues in the absence of friction. Eventually it will slow down. So when the string makes an angle to the vertical, the tension has a component in the horizontal direction. So you're going to have like your pendulum bob that's here. So you're going to have like an F of T. You're going to have your F of G. Well, really you're going to have FG of X and FG of Y that will be working on it because it's at an angle. Agreed? It's not moving straight up and down. So you're going to have many different forces that are working on here. So the angle of the string gets smaller and the horizontal component will decrease as it swings back down to past its equilibrium position. Okay, so the acceleration thing, I was just telling you about this. Acceleration is proportional to the displacement from the lowest point. In other words, highest acceleration at the lowest point of its swing. That's where the KE is going to be the greatest. The KE will be the greatest at that position, right? Because it's moving the fastest. Then eventually you're trying to switch directions. Try to think about this in your head, guys. Look at your kinematic curve graphs, right? So you're showing me your velocity. You're increasing in the negative direction, or you're decreasing in the positive direction, right? Because if you're pulling it towards the right, then you're starting positively, but it's swinging towards the left and increasing. It passes equilibrium, cross over x-axis, and now it's slowing down as it goes towards the right, or whatever, okay? So try to make it make sense to you graphically, because that is going to be coming up ultimately in this unit here. Once again, speed will be greatest at the lowest point of the swing, so you definitely need to know that. As the pendulum bob passes equilibrium, the horizontal component of the tension is now acting in the opposite direction of the motion, thus slowing the bob down. Therefore, the acceleration is always directed towards equilibrium, which is called position O, as you see right here, position O. So here's just a breakdown of what the free body diagram of a simple pendulum would look like. Notice how it already broke down your FG of, I'll go with this. Your FG of X being mg sine theta, and your FG of Y being mg cosine theta, because they're being treated like hourglass triangles instead of bow tie triangles. Okay. Whereas this one then would have just been straight F of G. And then you would also have your force of tension that's working opposite direction of motion. Okay, to analyze the oscillation of a mass spring system. If a mass is hanging on one end of a spring and is lifted up, so here's this mass that is hanging on this spring, okay, and it's lifted up and then released, it'll oscillate up and down, and up and down. Agreed? So the weight meaning the F of G, meaning M times G, is acting on the mass. It remains the same throughout, so this is going to be your constant on here. Your F of T is going to be the tension in the string. So in essence, we have an F of T that's working opposite F of G. Changes due to how far the spring is stretched or compressed, I guess we could say there, and tension is proportional to that extension or that compression. So looking at this, you will see some differences here. Please keep in mind about your, I'm actually going to turn this one on its side for a second. Notice how your force is opposite direction of motion. So if you are being compressed, your force is moving that way. This is going to lead us into an equation here in a second. This is Hooke's law. That's exactly where I wanted to go. Presence of a restoring force, because you want to restore, you want to go back to equilibrium, which is working opposite the direction of motion. The goal is to get back to equilibrium position, and the way you're going to do this is by saying F. Sometimes you see a K here, sometimes you see an S there, sometimes you see something completely different. I'm just going to call it F equals negative quantity KF. Now remember, this negative here is going to imply that F and X are in opposite directions. That is terribly important to remember, guys. This K value, what's this K all about? This is your spring constant. Every spring has a constant value on it. The stiffer the spring, the higher the K value. The looser the spring, the lower the K value. So looking at this spring constant, you're going to look at the greater the force needed to stretch that spring to a given distance, to try to pull away from its equilibrium position. So this is just a little note to remember. F is not a constant, but it varies with position. Okay, it is not a constant. Acceleration of the mass is also not a constant either. So we cannot use your equations for kinematic motion. You'll see that here in a second. But guys, really, this is what I want you to focus on. Make sure that this guy makes sense. Real quick though, remember this is what I was talking about. Who cares? That just means that the object was at rest when they were talking about that, because that's the static. You could see it as F of K either. But what I really want you to think of is this. Please do not read it as Fkx. That is not true. Your spring constant is not always going to be negative. What it is trying to say is that your displacement and your force are working opposite each other in motion. So this is our last slide here, and unfortunately you can't see every question. Let's see if I can manipulate this a little bit. Okay, fantastic. So what I want you to be able to do here is now use the first, like part 1, 4.1 part 1, and 4.1 part 2 to be able to figure these out. State whether the following are examples of simple harmonic motion. A ball that's rolling up and down a track, up and down, up and down, up and down. A cylindrical tube that's floating in water when pushed down and then released. Is it going to bob up and down? A tennis ball bouncing back and forth across the net. How about a bouncy ball that's just bouncing along the ground? Do those display simple harmonic motion? Periodic motion, repeated along the same path, oscillations in other words. And then please solve out these two problems. A pendulum completes 20 swings in 12 seconds. So what is the frequency? First you're going to have to get what the cycles are, which is your time period, t, and then 1 over t would give you A's answer. And then use your angular frequency equation to figure that out. Then if you want to be ostentatious, let's just say that it's 1.00 meters is how far this mass spring system, pendulum, decided to move, and then you'd be able to solve for the acceleration due to angular frequency. So this slide right here, the last slide in your packet for today, is what I would like you to do for your 4.1 worksheet. Okay? All right, so that is all, guys.